You clicked because you want to know about C extensions for AI pipelines without getting burned by build nightmares. The real problem is that most engineers assume writing raw C code is the only path to speed, ignoring how it breaks portability and turns your continuous integration into a fragile mess. By the end of this video, I will show you why relying on handwritten C extensions often costs more in maintenance than any performance gain provides, and exactly when you should reach for modern compilers instead. The industry has long operated under a simple heuristic that C extensions are always faster than pure Python or JIT solutions. This belief drives countless junior engineers to spend weeks configuring build environments just to squeeze out marginal speed improvements on data pipelines that could run efficiently elsewhere. The reality is far more nuanced because the bottleneck in modern AI workflows is rarely raw CPU cycles dedicated to calculation loops. Instead, it is often memory layout inefficiencies and serialization overheads that kill performance before you even touch a single line of C code. When you write a custom extension using GCC-specific extensions or non-standard headers, you create a vendor lock-in that breaks your build pipelines on Windows or macOS immediately. This forces teams to maintain separate configurations for every operating system they support, which is an unsustainable burden when iterating rapidly on new models and data structures. Consider the rise of alternative compilers like Cython or Nuitka as viable middle grounds between pure Python and static C extensions. These tools allow you to write code that looks familiar but compiles down to optimized machine instructions without requiring deep knowledge of the Python C API. The distinction matters because these modern approaches handle the tedious boilerplate work automatically, letting you focus on algorithmic logic rather than pointer arithmetic and reference counting details. Numba in particular excels when your workload is dynamic or iterative, as it generates optimized code just in time during execution. This means compilation latency gets amortized over thousands of iterations, making it often faster than static builds for numerical kernels where the data shapes change frequently between runs. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. However, you must weigh this against build times and dependency management complexity in a continuous integration environment. Static compilers like Cython or Nuitka impose higher upfront costs because they require full recompilation whenever your source code changes, which can slow down development cycles significantly compared to interpreted Python. This trade-off becomes critical when you are deploying across multiple platforms with different compiler toolchains available on each machine. A team relying heavily on GCC-specific extensions might find their pipeline failing silently in a Windows environment where those specific headers do not exist or behave differently than expected. The lack of standardized benchmarks comparing these dynamic optimization strategies against static C extensions leaves many practitioners without definitive data to guide architectural decisions for production-scale AI pipelines. Recent developments suggest that the language you choose may be decoupled from the final binary's performance, complicating your decision matrix further. Emerging tools like SlimC and Ghost demonstrate that portability is no longer a bottleneck even when targeting C23 standards or reducing header-only boilerplate significantly. You can now write high-level code in functional languages like Rust or Haskell and leverage compilers to generate standard C interfaces for Python Interop without sacrificing safety guarantees. This target C strategy allows you to keep the robustness of modern systems programming while leveraging the ubiquity of the C runtime that every major AI framework already supports. It effectively shifts the burden from managing complex build configurations to writing safer, more maintainable source code in languages designed with long-term stability in mind. The heuristic that manual assembly control or specialized compilers are necessary for peak throughput also requires re-evaluation based on actual workload characteristics. Tools like Magus and high-level assemblers reveal that compiler optimization flags often obscure the specific instruction choices needed for vectorization, making it difficult to achieve maximum performance without deep intervention. For many data pipelines, standard C logic combined with conditional compilation guards provides sufficient speed while ensuring the codebase remains testable on desktop environments during development. This hybrid approach allows you to enable platform-specific optimizations only in production AI deployments where those gains are truly necessary and measurable. It prevents your team from over-engineering solutions for problems that do not exist, or solving them with tools too heavy for the job at hand. The critical insight lies in understanding that portability is often more valuable than raw speed when building sustainable software systems. Relying on GCC-specific extensions creates a vendor lock-in situation where switching compilers becomes impossible without rewriting large portions of your codebase. In contrast, using header-only abstraction layers like Ghost eliminates configuration overhead while maintaining zero runtime overhead for performance-critical sections. This means you can write portable C23 features and use type-safe polymorphism in Python wrappers without the friction of managing distinct build configurations across Linux, Windows, and macOS simultaneously. The ability to generate optimized machine code on the fly often matches or exceeds handwritten C extensions in numerical kernels without introducing the portability friction that plagues traditional extension development strategies. This shift changes how you think about performance engineering from a singular focus on speed to a holistic view of maintainability and deployment reliability. When you adopt this framework, your CI/CD pipelines become more resilient because they no longer depend on obscure compiler flags or platform-specific behaviors that break under minor environmental shifts. You gain the confidence to refactor code aggressively without fearing that every change will require recompiling across 3 different operating systems with identical results. The long-term maintenance costs for hybrid stacks decrease significantly as you reduce the surface area where build failures and compatibility issues can occur during production deployments. This approach ensures your AI pipelines remain fast, portable, and easy to update as new tools and standards emerge in the ecosystem. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.